Okay. Well, thanks to everybody for the good turnout here at the Physics Colloquium. Today we have the great honor of hosting Professor Sergio Carbajo, who is from electrical engineering, but also holds appointments here in the Department of Physics and Astronomy, and also at SLAC. It's the National Laboratory up at Stanford. Sergio's career, I think, we could spend a lot of time on exactly what his background is. It starts off humbly enough in San Sebastian, Spain, and in the Basque region. We had the pleasure of hosting a conference in Sergio's hometown over the summer. He then went off to obtain his training in various different places around Europe and the United States, doing a joint PhD between Hamburg and Daisy National Laboratory there and MIT. After a stint at SLAC, where he made his impact on the free electron laser program and various aspects of ultra-fast science, he landed here, and we're lucky to have him. So we could probably just at this point echo Sergio's title and say lights, camera, action. Let's give a welcome to Sergio Carbajo.
Thank you. Yeah, thank you, Jamie. That's a really warm welcome. Jamie and I have known each other for a long time since I was a student, and it's a really, it's really a pleasure to be here. I'm part technically of this department, but I don't get to interact as much. So I really appreciate the invitation. Happy to see a lot of familiar faces, and also not some of them that are not as familiar. But yeah, let's talk about what this presentation is about. And I'm trying to target a broad audience. First of all, I just want to acknowledge, as Jamie mentioned, we're a growing group, particularly at UCLA, but I spent the last 7 years at SLAC, and so we actually co-located. We never really quit our work there. We're just trying to move more to academic research and then use some of the research that we have here at translation to facilities. But at the core of what I'm doing, and this has been a heavily used analogy, so if you've seen it, I'm sorry. But we're both trying to borrow the both artistic and technical skills of Edward Muybridge, who may or may have been, but it's credited to be as one of the first people that sort of enacted what we call stop-action movies. The idea of freezing the motion of something moving in time and space to answer some fundamental question, fundamental-ish. In this particular case, it was not that fundamental. It was a bet between, at the time, governor of California, Leland Stanford, and another sort of a tycoon of the era as to whether a horse would lift all four hoofs at once while galloping. And so they task Muybridge with this image, and you can see that right here, this particular horse at least does lift all four hooves, right? So this is the kind of questions that we try to answer by sort of using the premise that seeing is believing, and you might build really complex models for your systems, but sometimes you just gotta contrast those with actual data or simply visualize things in motion. Just a little thing that is not really said a whole lot in this type of analogy. This man, Gilbert Dome, happens to be also the first Black person featured ever in a stop-action movie. We usually just talk about Sally. But that's the essence of what we do. So we're trying to do the same thing, take stop-action movies, but of the quantum world. And here there was an earlier question instead of the Q&A preceding this talk as to what we mean by quantum. And this is, broadly speaking, some systems that we could treat in a quantum world. Also, classically, we're talking about the interactions of electrons, atoms, molecules, and towards macro scale systems. But we're looking at the dynamics, right? And why is this important? This could be argued against and challenged. Okay, so the premise of the people like myself that are working in early dynamics, and for example, the Nobel Prize in Physics this year for attosecond dynamics, is that we say that certain aspects of how functional materials may behave relies on the early dynamical relationships between different constituents of matter. So that means how electron dynamics occur at attosecond timescales might affect how atomic or molecular systems, especially small molecules, might behave and the femtosecond and picosecond timescales. And then you can begin to sort of up that scale to larger systems that may be functional devices, MEMS and NEMS, and what have you, right? And so what I'm trying to draw is that usually in nature, there's a direct corollary between space, the dimensions of things, and how fast the intrinsic or inherent dynamics are. Some things are really, really small and energetic, tend to move really fast. Things that are large and like elephants, tend to move small. So you can move up the ladder and see how these different sort of space-time domains might affect each other to answer either basic questions in chemistry and biology and functional materials and so on. So this is the premise, right? Seeing is believing, and looking at the early dynamics of elementary constituents of matter might tell you something about how things will behave, or even control how things will behave. Yeah. So I'm going to cheat here, and rather than speaking, I'm gonna play you a video made by my friend Greg Stewart at Slack to explain how this works. Actually, this idea of making molecular movies. And let me unmute. Give me a second.
Most like
Is that interesting? Yeah. Let me try this one last time, and if not, we can move on. I have another animation. All right, I have another animation. I'm sorry this is not working out. I was excited to show you this good video. I'll show you just a video without the audio, and I'll just try to narrate it.
The first process kicks off.
What you wind up having is sort of, am I not sharing? Never mind. Good. Give me a second. All right. Once and for all. So what you have here is basically a system where we draw on how we do the stop action movies. You have your molecular system in this case, and at some point you got to initiate the process. So that's done, for example, with this laser. That initiates some dynamics, and now you can capture the specific frame and time and space by using, for example, a secondary radiation source. It's another laser, or in this case, X-ray beams or electrons. So what you wind up having is initiating the same process again. When you trigger the dynamics to say initiate dynamics, right? Start moving, and you wait a specific amount of time to capture a frame. If you do this enough times with different delays, you can capture some sort of stop action movie, right? So this is a bit of an analogy. Clearly, it's a rendered sort of motion, but this is not too far-fetched from the actual data that we take. Okay, so this gives you a bit of an idea of how we do this. So moving on to the next slide, whenever I can to do that. Following this process, we've been able to sort of enact certain breakthroughs in life sciences and chemistry, for example. Something that has become truly revolutionary is that by taking different images of the system that is called photosystem 2, we've been able to sort of analyze and reconstruct the motion of this macro protein, so photosystem 2, that is basically in charge of harvesting light from the sun. And every time it absorbs a photon, it undergoes a different conformational change that is in charge of oxidizing water, basically creates ion channels that are then used by cells at a longer time scales that is well understood to be part of the ATP, the energy that cells use for cellular processes. But this process, this cycle was theorized in many different possibilities. There were many different pathways that were explored, and it was multiple years of experiments trying to take different snapshots as this cycle occurs that unveiled which one of the different theorized pathways was actually the right one. Another example of recent breakthroughs is, you can look at chemistry and organic chemistry, for example, how things isomerize, how they vibrate, how they may dissociate. on the different light excitation, and you can take pretty good snapshots of these different molecular dynamics and see whether there is particular pathways, for example, to reducing hazardous waste. One key example might be, can you dissociate CO2 or any hazardous waste, for example, into something that is not harmless and has an added value product, like capturing carbon into, for example, a diamond or graphite, right? So these are some of the references that you may look if you want to learn more about these. But let me now, this is kind of my introduction. Let me now zero in on two things. One is, okay, what kind of instruments can you build to do these experiments? They're very complicated, and we have some faculty here working on those. And then on the second half of my talk, I'll speak more about the emerging science cases that we're working on in my group and other collaborators. So something that we try to work on is on unifying lasers and accelerators. That's broadly speaking two fields that are coexist in many different applications, but they don't tend to talk to each other a whole lot. And so we're trying to bridge that gap. One clear example of that fusion might be any sort of plasma or laser wave field acceleration devices, for example, some way to provide charged particle beams for high energy physics, for example. Some people postulate using some of these for medicine or proton therapies, for example. The second one that I want to bring, these are just prominent examples, they're not the only ones. It's X-ray free electron lasers. This is the one that I'll be zeroing on. And this is a way to produce hard X-rays to its extreme. Of course, you can do, there's all kinds of FELs, even terahertz and UV, but producing bright and short snapshots, right, to capture images, as such as shown in the animation, cannot be done easily with current modern technology. And so sometimes you got to resort to these really complex facilities or compact equivalents to be able to have really bright X-rays that are coherent, like a laser, not just the chest X-ray sort of machines, those X-ray tubes that you can see in a hospital. So something that looks like a laser, but also has a really short duration, right? That's at the heart of how you can make these experiments work. So a little story for those who are experts in X-rays here, little short tutorial. All you got to do is, this sounds simple, but all you got to do is put an electron bunch that's traveling at some decent speed, usually relativistic, into some undulator or something that makes this electron beam wiggle. As you might know, if an electron, a charged particle oscillates or it's made to bend, it will emit radiation. So this is a bit what happens in the first few cycles of this undulator magnet that it's basically changed in its polarization. It will start undulating while it propagates forward. And so at that point, you just have simple electrons or photon emission that matches somewhat the strength of that undulator and the speed of that electron. So you can control the photon energy that comes out. But as this is happening, if you've studied any laser physics, it's equivalent to the SASE process. It kind of starts from noise. One of the electrons starts emitting one photon, the next one does. They're kind of disordered, they're incoherent to begin with, but they can still building up to kind of interact with electrons back and forth. The electrons are quite relativistic, so they're going almost at the speed of light. The photons are coming from behind, catching up. It winds up happening that they get bunched up, and at that point, you can actually have coherent excitation where the FEL becomes an actual laser in the sense that its intensity scales with the number of electrons squared, right? So if you're able, for example, to start with an electron bunch that is already bunched in the longitudinal way in the right periodicity, you can avoid SASE, and you can start amplifying directly, right? But that is a bit how these work. This is a fourth generation sort of facility in terms of accelerators. There's all kinds of other accelerators you might be familiar with, like synchrotrons, for example. There's different generations of synchrotrons as well, but this is showing you basically how you can access keV level photon energies. This is hard X-rays with an incredible amount of peak brilliance compared to prior sort of sources that are existing. And then HHG is kind of right in here. I'm bringing it up because of the Nobel Prize in Physics this year for attosecond science. It really is a Nobel Prize for HHG as a technique that can provide actually attosecond pulses, but it can't really be scaled up in photon energy to hard X-rays, and at least not in very intuitive ways. People have been trying. So I wanted to, this is going to work because this is an actual animation. I wanted to zero in again on how this is done and probe the audience a little bit. I get tired of speaking for too long without asking questions. And so, I want to kind of provide a little more of an ingredient to how we can build these kinds of images, right? I said that you have some sort of sample, right? it's idle there, and nothing's happening to it. If I shoot an X-ray to it, I may get an image based on diffusion, right? But I'm not getting any dynamical data. Meaning, if I shoot it to the next target, if they're all the same, I'm gonna have the same data, right? So let's kind of see a little bit what the ingredients actually are for these snapshots to be able to be taken. The pump system, the thing that initiates the dynamics. What can those be? Can anybody raise their hand or speak out loud? What are my ways to excite a system?
Optical laser.
Yeah. Why would you choose an optical laser, for example?
If you want to look at like like plant photosystem proteins, you would want to illuminate it with the kind of light that it responds to.
Yeah, that's a great idea, right? If I have a system that does react to light in the way that I want it, then I shine it with that light. In the case of photosystem, it was green photons, actually, just to represent. There might be another practical reason and perhaps a cheat way to use optical lasers to do this. Can I excite something? I mean, if I want to ask you to excite a system however you want it, but do it really fast, do it with a femtosecond pulse, a femtosecond excitation. What are your options? Can you do it with I don't know, like a voltage supply? This, even at the best ones, the rising time might be, picoseconds or so, right, at best.
Electron beam?
Yeah, electron beams can be really short if you make them packed, right? So when it comes down to really trying to initiate things at really fast timescales, your options are really, really limited. So sometimes, if you look at some of the breakthroughs that I presented, there are rhodopsin, for example, in biology and photosystem, actually systems that respond to light in a way that is natural. But sometimes you use lasers just because it's the only thing you got to excite things, and you deposit, for example, an electronic excitation, and you hope to excite a phonon or some other quasi-particle, right? So options still are limited. That's the one thing, the pump, right? And then the probe, I already sort of alluded to using X-rays, right? Why would I want to use X-rays to look at molecules and not another optical pulse? What do X-rays? Yeah, David.
Gives you nice resolution.
Yeah, exactly. If you talk about imaging in general, this is a generalized statement, but if you're talking about imaging, your spatial resolution tends to be limited to lambda, whatever lambda is. If lambda is 1 micron, you're going to be around 1 micron resolution. You can cheat it maybe by a factor 2, 3, or 4, but not much more. Same thing, if you want to look at electrons or electron clouds or atoms, you need to use angstrom level wavelength. That's just a generalization, right? There's a lot of caveats to that, but that's why you want X-rays. You want them coherent to be able to trap something here that might have coherence. You don't always have to have coherence. And then so the X-rays give you the spatial resolution. What is the last piece of the recipe to be able to get short snapshots in these X-rays? Is it sufficient for it to be an X-ray laser? Do I need to have any considerations as to the time shape of that pulse? Yeah, as short as the dynamics that I want to see, right? So if I want to see atomic dynamics or molecular dynamics, it probably needs to be femtosecond-ish. If I want to be seeing larger things, it can be longer, right? So it's no different from having the shutter speed of a camera. It's just equivalent. You just need to make your pulses really, really short. And then it comes to detection. In this case, we're looking at diffraction, for example, right? How light will, X-rays in this case would interact with electron clouds and would form some sort of image. If I'm talking about crystallography, it might look differently. And so we actually have 2 volunteers to show us how that looks. So I just want to, show you for those of you who don't know what crystallography might mean, we can turn on a laser, for example, right? Let's say that these are 2 probes, right? I'm going to cover my eyes. I have a molecular system here, right? And I'm going to try to capture, if there's nothing here, the laser is just going to go straight through. So I build these detectors with a hole right in the middle. But the moment that I put something with a periodicity, for example, a quantum system that has a periodicity, or something that has a periodicity in the order of lambda, I will obtain some diffraction pattern, like that. Yeah, there you go. And so, yeah, thank you for doing this. So, the thing at the center is your 0th order, is whatever light goes straight through is not interacting with your system. But then all those different peaks that show up here are somehow telling you some periodicity, at least projected in 2 dimensions of the system that you have. So if one of you, for example, could rotate the sample that you're using to see that this pattern actually changes. It might not be bright enough, but you can follow some of the bright dots and, yeah, keep rotating it strongly more and more. let's see where this goes. Yeah, if you follow, for example, some of these dots here, you see that they get closer together and then they expand. Basically, by rotating the sample or rotating in different directions, if you capture many of these images, you can reconstruct the three-dimensional shape of whatever you have, if that makes sense. Now with a single shot will be a projection, but if I randomize the orientation of my system, I can always back reconstruct with some sophisticated but well-established algorithms what this is. And then the other reason why we have two colors is to show you that you can play with wavelength to see the two systems that they're using are the exact same, they have the exact same sort of atomic or periodic structure. But this tells you that using the wavelength, as you should know by Bragg equations, gives you a different sort of angle, right? So X-rays can provide you with, depending on choosing the color of your wavelength gives you a knob for seeing whether I want to pay attention to peaks that are further away and focus on this type of resolution scale, or I want to focus on early scale. So hopefully this demonstrates a little bit of how diffraction occurs. We just do that with X-ray pulses that are really short. That's all we do. Yeah. Thank you to our volunteers. And so, going back to the role of how can we make these, this is sort of the state of that, right? How these facilities work. Now, our role in trying to make these facilities better kind of tap into multiple different aspects of the instruments. So to first order, what I wanted to say is like, okay, we're talking about unifying lasers with accelerators. First and foremost, lasers in most cases are in charge of producing the electron beam off the bat, the electron beam that gets accelerated to multi-GeV levels or MEV levels, right? So shaping laser, for example, at the photocathode level, either wavelength, spectral, temporal shaping, can affect the electron that you start with in your facility that then inherits properties that might determine how your X-rays might propagate, might inherit from the electron beam. Another example of how lasers can be used to manipulate electron beams is later on, after you generate them, you can couple them in, for example, undulators to add high frequency sort of modulations to its phase space distribution, and be able to, for example, laze at harmonic frequencies of the lasers that interact with the electron beam in the X-rays. This is called, one of these techniques is echo-enabled harmonic generation. So this is a way to generate harmonic wavelengths in an X-ray. But these are just two examples to say you can use lasers to control the generation of the electrons, or to control the electrons later on after they're generated. And this is the basic premise of how we interact with this facility. So to give you an idea, this is a cartoon schematic of LCLS where you generate the electrons right here. They get accelerated to some 120 MeV or so. There's a shaper here, an undulator, and then this is the rest of the facility. These are the 2 miles, and you finally have the undulators here to produce X-rays, right? This is where you wiggle your X-rays. The first undulator in this case, for example, can be sassy, as I shown you. You start with electron bunch as is, unbunched, so you start from noise. And then you can actually seed it the same way you can seed a laser to sort of amplify further or reduce the spectral content of your X-flows. So to give you an idea, this is just one of the applications. This is at the intersection of laser shaping and electron beam shaping. We've shown that if you use a donut beam right here on this undulator, rather than a normal Gaussian beam to shape the electron, basically if you put a light beam that has a channel, a null right in the middle, a donut, that propagates with an electron beam right at this undulator. I don't want to get too jargony for those here that are not very familiar with these terms. Where you can make the electron beam energy, this is the phase space of electron beam energy, the longitudinal phase space. This shows you essentially how much the energy modulation is of the electron right here at the end. It's really spiky, it's really noisy here. You want to avoid that. The X-flow can laze basically when the electron beam energy is really thin here. And so we can improve this distribution. We can smoothen it by making it go through this channel. And as a result, you can go with a type of spectrum. I think I have a zooming here of your X-flow that without the donut is this red shape that you have. And if you look at the X-flow and sort of in its spectral domain, it's really noisy because it's usually born out of SASE. It's not longitudinal coherent. You can imagine that every electron is kind of emitting its own, photon, and then there is some coherent construction, but you do have the coherence is spatial but not longitudinal. You wind up having shot to shot. You have somewhat of a bit of a noise, and if you're trying to run, for example, an experiment that requires a one specific color and that peak to be really strong, then you need to resort to sophisticated methods like this one. And so what we're able to show, for example, is by smoothing this energy distribution of the electron beam, making it go with a donut, we can have really high spectral purity X-rays that have some longitudinal coherence that can be important for Zorm experiments. But I'm bringing this up just to tell you, a little bit about the types of experiments that we tried around the facility. Clearly, there's hundreds of people involved here, and so our expertise is in how does laser shaping support the facility, either in enhanced modes of operation or new modes of operation. And so to bring more examples to this is for nonlinear optics enthusiasts. Something that we do know is that if you run the electron beam at LCLS here with a UV pulse that has a flat top temporal profile, this has been a forever sought after flat top. It might seem easy at first sight to generate a pulse like this, 20 to 60 picoseconds in the UV, but believe me, it's not. Many people have been trying for a long time. And the reason why this is sought after is because in these types of facilities, this creates linear space charges that allow you to compress the electron beam better. Let's just leave it that way, or reduce the emittance of electrons, so to speak, as momentum space. Yeah. So you can, I'm happy to answer questions. I don't want to get too deep into that. One of the things that we've done is come up with a technique where you can mix two IR pulses with specific dispersion terms in the second and third order at a nonlinear crystal. We're using good old some frequency generation. But when you mix this by combining the right second and third order dispersion terms, what you can have is a sort of a naturally narrowband some frequency generation signal that has this shape. And the shape basically can be controlled by adding different second and third order dispersion terms. What does this do? It creates basically in the UV or in the green or whatever color you want, a pulse that looks somewhat flat top like. In this case, this will be its spectral equivalent. The reason why I'm showing something that is not exactly flat top is because we discovered in running start to end PIC simulations that these are basically heat maps that show how much your emittance. I'm sorry, this gives you, emittance is a number that you want to minimize, okay? You want to minimize this number, and it so happens that if you have a perfect flat top, it's not as good, and you can achieve some better values, about a 25% improvement over the emittance with a flat top or a Gaussian when you have this kind of shape. So this is not tested yet, meaning we've developed the laser and we can generate these pulses, but they're not tested at LCLS yet. So this is just a promise. This promise is that the electron beam at LCLS can have a reduced emittance of 25%. But what does this mean? Is that more or less the X-ray wavelength that we can emit up until now, the cutoff wavelength can be extended by 25%. That means that if my cutoff wavelength at LCLS is 10 keV, that's a maximum wavelength I can emit. By playing this trick upstream, we might now be able to emit at 12.5 keV, which is quite a leap, right? So there's a lot of efforts involved in this emittance reduction business, and this is one of them. This is just to show you, this is actually old data, but this is to show you the experimental demonstration of something that looks quasi-flat top. Why am I presenting this? Another thing you can do with the UV shaping, right? Shaping how the electron beam comes out is that you can add tiny little modulations. For example, right here, you see there's a little dip, which you can use to drive an electron distribution that might self-compress. Kind of you drive an instability of electron beam. Imagine an electron ball, right? These are electrons that up until they get relativistic, they hate each other. They're repelling each other. They're unhappy. You can actually exploit that unhappiness to have part of the bunch affect another part of the bunch and sort of push it forward such that you, by playing the right tricks, I'm making this sound really easy, by the time you reach the andulators, you have a spike in the electron beam density that is at the right energy match for the FEL, so that only this spike lasers. And so this is how we generate attosecond pulses at XFELs these days. This is relatively new work. Even alumni from this group, from Jamie's group, Aldo Marinelli and other people are involved in this. When I talk about attosecond, we're able to produce maybe hundreds of attoseconds, sub-femtosecond pulse durations in an XFEL, which is quite remarkable. And it all relies on one way and another, not only this way, by exploiting some instability in the electron beam, by imposing a modulation in its density profile. Okay. So, following this recipe, we kind of want to come up with, just to give you an idea, this was a 2 years long project and it's a static shape. It's really hard to make this modulation change. So the question comes up, okay, can we be smarter about this? We laser physicists after all, and so can we take a traditional CPA laser, actual pulse amplification system that is used, for example, at LCLS, to develop smarter shaping techniques, for example, with programmable devices, such that we can, produce shapes in the UV domain that look in any particular way that we want to. Do we want a flat top? Do we want a triangular? Every one of these shapes has a different application, either at expos or other facilities. This is not just for expos. So we've been able to develop over the years a very comprehensive start to end model that takes into account all the sort of physical principles of any of these lasers, from mode-lock lasing to amplification to shaping. And this code is actually modularized in a way that you can move it around. And it not only helps us be able to reverse engineer some of the lasers that we have in our lab, which has actually gotten us to some trouble, meaning we can reverse engineer commercial lasers. I can speak to that a little bit, but it poses a natural question, right? Which is, can I use, for example, neural networks or LSTMs to calculate these calculations are quite comprehensive, they're quite demanding. Can I speed these computations to not only reconstruct what I want, but perhaps inverse design my desired parameters? That means rather than buying a laser, playing tricks to be able to attain some sort of flat top profile and spend years on that, can I define the flat top that I want and back engineer either the nonlinear optical components that I need or the shapers that I need? And can I do that in a faster fashion, right? So this is a project that's adjacent to facilities that we're working on here at UCLA. In the same vein, something I didn't mention, but you can imagine these facilities are beginning to run at higher and higher repetition rates. And so UV damage, for example, is an issue. The quality of the beam can be problematic. And we have a new project where we're saying, okay, we can play with different nonlinear optical technique, not some frequency generation, but in this case, forward mixing using gas-filled hollow fibers, where we basically, these are just the three coupled equations for forward mixing. You have the idler, the signal, and the pump. I'm sorry for the jargon for those of you who don't follow, but basically I have this gamma. These gamma factors are something that tells me how nonlinear that coupling is going to be between these different waves, and this delta beta is going to be the phase mismatch. So how long can these waves propagate with each other interacting? And by playing the right trick, one gives you an idea of the nonlinearity, and two gives you an idea of the dispersion between these. We think, will yet to be proved, that we can shape the IR, which is something relatively easy to do with current optical technology, with a programmable device, and have that shape be transferred to any up converted or down converted signal in the UV, in the mid IR, in the terrace, whatever you want to. This is really not intuitive, right? You're using heavily nonlinear processes in order to map faces linearly to other components. And so we really, after this, is a holy grail because it can open many kinds of applications in laser shaping overall, not just for X-rays. And that's something that we're currently just testing right here at UCLA. And I'm probably going to run out of time quickly, so I'm going to try to go faster. But to not give you the idea that all we're doing is work in large-scale facilities, right? We're after, like many other people, and can we make some of these more compact? They don't need to be X-rays. They could be X-rays. Jamie's working on that very heavily for many years. We're taking one approach in collaboration with other people as to saying, okay, can we make this much simpler? Instead of trying to think, okay, can we make these X-rays really, really small? Can we reduce the electron beam energy, make andulators are really small, what have you? Can we just go the opposite route? Can we borrow good old X-ray tube technology? An X-ray tube is no more than just some electrons accelerated. They hit some targets, say copper, tungsten. They emit all over the place. This is how your X-rays in the hospital are taken. Okay. Can we do that? It's cheap. It's easy. Can we do that by? What happens if I take that electron bunch? This atomic system here is symbolizing that tungsten, the copper, what have you. What if we can create a coherent state of two electrons? For example, take the electron beam, separate it into two states that have a momentum, a different momentum distribution. For example, rather than the electron beam going forward, you create two states, and you make that momentum sort of curve. You change their K vectors. Can I have some enhancement of this Bremsstrahlung radiation, this X-ray incoherent radiation? I don't have enough time to talk about this, but when you create two states or end states, you can start suppressing certain emission angles, like you can see here, for example, with 20 kV electrons and 200 kV electrons. These are electrons that you can buy for, you can build yourself with your own equipment, or you can buy these devices for $10, $20, $50,000. By shaping the electron beam, we can show that, among other things, we can make that long and really wide emission angle be much more directional or longitudinal. If you add more states, we can show that we can make something that is really broadband, naturally branched stratum, be much more monochromatic. And so the take home from this is that what we're trying to study is how electron beam shaping, again, but non-relativistic electrons in compact devices can enhance X-ray emission. And I'm not talking about X-ray coherent lasers in this case, but just simply X-ray emission. There's a lot to be said here, but I'm going to go faster. The idea here is that rather than relying on undulation, you rely on good old photocathodoluminescence. This can be done coherently, incoherently, but if you take your electron beam and it's going to interact with some system, you can basically play with this transverse momentum space and the longitudinal one. You can think of this as a pancake. And if you play with these geometric factors, what you have here is this would be essentially the probability of an X-ray photon or any other kind of photon exiting from this interaction. So this is the probability of this photon coming out at a specific white solid angle, and then this small omega is at a specific wavelength. What you have here is something that depends on the number of electrons that you have, with an exponent of the longitudinal component that is proportional to, of course, the duration of the pulse, and another component that you can play with this geometry. Long story short is that if you make this pancake really, really short, you can make this become super radiant. What does it mean? That your emission angle probability is going to depend on n squared rather than just n. And this is how you can make this perhaps a little more efficient. Lots to be said here. This, of course, the title is a little bit misleading. This can be done in terahertz or in the X-ray domain, depending on how you play with this pancake distribution, okay? But I want to jump into some applications because we're talking about molecular films after all. So I think, I'm happy to take any quick questions if you want to. Otherwise, we can leave it to the end. Likewise, there's lots to talk about in terms of application. So I said this also in the Q&A earlier. I want to zero in on terahertz. Why not? So what can we do when we drive system with terahertz and then probe them with electrons or X-rays or other optical ranges? I would say in general, a different way of speaking about the science cases that we study have to do with looking at non-equilibrium phenomena. For example, how things become thermalized, how things lose coherence as they evolve, right? And there's all kinds of applications from high energy density sciences to biology and condensed matter physics. Now, let's just talk about some of the systems, and these are emerging. Here I'm being a bit more speculative in the rest of my talk. These are emerging projects that we're working on. So I'm happy to answer questions and be poked with some of I'm happy to be challenged. But the main motivation, some of you here are working also on terahertz, is that the terahertz domain is somewhat like you can think about photons with MeVs or milli-electron volt level energies, or really, really small energies. You can think of them also as really fast RF transients, like an electromagnetic field. So regardless, terahertz really interacts very strongly with matter. For example, it has lots of absorption peaks in most molecules in condensed matter systems, and the frequency tends to correspond to magnum phone and molecular vibration. So it is both difficult to generate, but it can also access a lot of energy, different energy states, right? So a quick sort of introduction, how you generate terahertz. I think there was a question earlier. There's many ways to do this. If you're using lasers to generate terahertz that are really fast and strong transients, and I should say terahertz here in the strong field, this is the SF. At the end of the day, what you have is trying to convert an IR laser into a terahertz laser. So this means you take a 1 micron laser, an optical laser that has a lot of power, and you access different optical rectification schemes. This is, again, some nonlinear optics jargon, but it all kind of depends, it relies primarily on difference frequency generation. You have two photons in the IR that are really close to each other. In fact, they're as close as a terahertz, for example, and they interact in a nonlinear medium. They beat such that you actually have the difference frequency of that beat come out as a terahertz photon. So you really need two photons to interact at minimum and beat at a nonlinear medium. And so all of these different approaches are different crystals, different media, and different tricks as to this simplistic beating idea. But if I were to separate them in two wide categories, at least for applications, is one of them is really narrowband, meaning it has a single-ish color, meaning the electric field has multiple cycles. And the other one is really broadband. You can see here is from 0 to 1 terahertz. Here would be from 0 to 1 terahertz. So this is about 20 gigahertz bandwidth, and this is about 500 gigahertz bandwidth, right? So this corresponds to a single electric field cycle and multiple electric field cycles. You know, so in a way, this can excite many modes in some molecular system, and this can be more selective. And you do everything by optical rectification, in some cases with multiple periods, in some other cases with a single crystal. Again, happy to answer questions on this, but to move on, you know, perhaps the most established way to generate really strong field turrets radiation is the second one that I'm showing you here, where you slow down the group velocity of your laser, your IR, by imposing a pulsatron tilt, and you need to slow it enough to match the phase frequency or the phase speed of the turrets. You might not know this, but you know the index of refraction of turrets in most materials is about 5, 6. It's really, really large. That means that turrets fields are really slowed down. So you got to slow down your IR a lot, and the only way to do this is by tilting it and reducing its group velocity significantly. By doing that, you can do basically what I just told you to do. You have this. Imagine this is my 1 micron laser or so in terahertz. It's about 370 or so as a given bandwidth. So you know that you need to have somewhat of a broadband IR pulse. And any two constituency, any two photons are going to beat this nonlinear medium to generate, for example, if these differences have a terahertz to produce that. Now, there is an interesting process that can be accessed here, which is cascading. And you can imagine that a 372 terahertz photon that beats and loses energy, you know, loses half a gigahertz, still pretty much a 772 terahertz photon. It barely lost any energy. So you can recycle the same photon many times to keep generating terahertz photons. And this is how you can get relatively high efficiencies, because you're really moving a factor of 300 and the photon energy, right, for 300 terahertz to 1 terahertz. But your efficiency can be better than that. It can be about 1%. And it's because you can beat what we call the Manley-Rowe limit. The idea that the same optical photon can beat multiple times to generate terahertz photons until it's lost sufficient energy or it's walked away enough from the terahertz that it no longer interacts. Yeah. And so following this trick, this is not new. It's been around for a very long time. And so what's at the heart of this really is, you know, following this trick over the last several decades, we can generate, this is a lot of energy, about 14, 15 millijoules in the terahertz using optical rectification. Now, what's the real effort here? It's not in this trick. It's in building bigger, more powerful lasers, right? So this goes back to using lasers, for example, NIF level, high investment. And so the real technology behind all of this is in laser development and not necessarily in the technique. There's some tricks involved with that. Now, so finally moving to applications, I wanted to position water as a central element for how we can drive chemistry and biology using terahertz. And that is because terahertz interacts really strongly with librational modes. Libration, this L is not accidental. It's a very fundamental sort of mode of a water monomer that can basically, in this picture, we're going back to non-equilibrium dynamics, when you shoot a terahertz pulse into water, what you might expect in the really fast timescales is that there's some non-equilibrium condition, right? You start agitating these molecules. They might all get aligned with the electric field of terahertz, depending on the wavelength. And then after some hundreds of picoseconds and nanoseconds, you can actually talk about a temperature jump. So energy has been deposited, and sure, this is a system in equilibrium. And we can exploit the mechanisms from non-equilibrium all the way to thermalization, how exactly these molecules vibrate to control different physical processes. And so to give you some examples, we can control protein folding with terahertz, not by affecting the protein itself. You see here an enzyme surrounded by all these little dots are basically water molecules. By affecting the first few hydration shells of the water, you can affect protein motion. I'll speak to this in a moment. You can affect also, you can work on chemical engineering, as I mentioned, for example, by creating supercritical like water structure, one where there might not be as much temperature yet, but you deposit enough energy that the equivalent temperature is really high, but the water doesn't have enough time to evaporate yet. You know, in picosecond timescales, things are still keeping together. And you can also use it to control not only superheat, but also supercool water and explore new phase states of water. So I'm gonna go through this relatively quickly because something that we know, you know, I just mentioned the same thing. Something that we know is that terahertz in general can, you know, mid-infrared to terahertz, I'm being really broad with this range, can affect different librational or rovibrational modes of water. So you have stretching modes of water at different peaks. This will be about 2 micron, the bending modes. And then librations come later on after 7 microns or so wavelength. And we demonstrate that we can heat up water and some equivalent temperature jump over a few hundreds of femtoseconds by adding this, few cycle terahertz pulse with, it's not here actually. This is a 10 micron source of 30 terahertz. It's about 10 to the 14 watts per square centimeter. It's a decent amount of energy, but it's not impossible. And going back to expos, this would be basically, if you can imagine this, the 1 or the 0 being the center of the detector that I showed earlier with rings. These are different rings that show up as a function of time when I pump the system with terahertz and I capture with X-rays. And these rings sort of breathe as you move through time. Negative time here is before X-rays, before the pump. And then this is all in femtoseconds. And what these curves, these peaks are showing you basically is how OO and OH distances are changing. These peaks will move depending on those atomic distances. So we can retrieve already the motion of water under these circumstances. And using this trick, we can basically correlate using either synchrotrons or expos with some sort of X-rays and biology, many effects that have to do with reorientation times of proteins and DNAs or crowding effects, meaning do things behave differently when, for example, two enzymes are really close to each other under the same conditions. That's what we refer to crowding effects. Or does the orientation matter with the polarity of, for example, the terahertz, because the water will be vibrating following the electric field of the terahertz. So this calls for basically an idea that we can perturb. What I'm beginning after here is that in biology, for example, among other things, we can perturb the hydration dynamics, not the protein or the enzyme itself, but the water hydration shells surrounding it to try to control the function of biomolecules. This is I think a thought-provoking idea, and we just published this in Nature Chemistry a week ago, where we take, these are basically the images that you can take at a normal facility. So this is your actual detector. You pump your system with an IR. In this case, it's a mid-IR source. You initiate some process. We hit a resonance that we know doesn't exist in the protein that we're trying to study. And then we take two kinds of images. You cannot see it here, but these diffuse rings come from the diffuse water scattering. These are the peaks that I just showed you that can breathe. And then if this, if my image quality was good enough, you would see constellations here, like the ones that our volunteers showed, that come from the crystal itself. So it's easy to discern what is solution and what is the crystal. Long story short, by playing this dynamic, we were able to, these are the protein max that you can actually reconstruct from these types of images. When you reconstruct the view, these are the the electron density maps. Blue means you have an increase of electron density, and yellow means you have a decrease of electron density. You can follow these dynamics. What we've shown is that this particular enzyme that was a model binds to an inhibitor when there is specific temperature jump applied at specific frequency. Meaning when I shine this with, say, a 3 micron laser, this protein is going to be likely to bind to an inhibitor. However, if I shoot it with a different wavelength, even if the temperature jump is the same, it will not bind to the inhibitor. This might be, I'm trying to make it really simple. This might be the idea that says, looking at non-equilibrium dynamics simply from a temperature jump standpoint does not tell you the full story. And this is kind of ratifying what I said earlier. Adding a 10 Kelvin, for example, temperature jump and allowing an inhibitor to bind to this enzyme doesn't happen under any kind of 10 Kelvin jump. It matters how those molecules move around the hydration shell and overcome the energy barrier of that particular protein. And we chose lysozyme in this case with an inhibitor because it's a good model protein that we understand quite well with human function. So this opens the possibility, and I'm being very speculative here, to say, if we understand the biological function of certain proteins or enzymes, which is not my job, we might be able to control whether they get activated or deactivated by simply shining, for example, light onto them, and not just with a temperature jump, but understanding how the water dynamics surrounding them in solution might affect these dynamics. So there's a lot of work happening in this regard. More beam times. Please ask questions if you have them, right? And then maybe even more speculatively, a project that we just started we got a grant recently is talking about chemistry. So let's forget about biology for a second, and let's keep thinking about how terahertz, if I crank up the energy of the terahertz, really, really strong field, I might be able to create extreme conditions of matter, right? Like what I mentioned earlier, supercritical, like water and what have you. So imagine in this picture, I have the water, right? These little guys have some electrolytes, perhaps maybe a hazardous waste, some inorganic molecule. And I may, for example, have also some nanospheres if I want to have some sort of field enhancement. The questions that we're trying to probe here are, if I use terahertz in a domain where my in any, for example, of nanosphere or enhancement structure, when I use really long wavelengths, I can basically approximate the electron temperature to the lattice temperature. Modeling this is relatively straightforward. We can begin to ask questions and drive experiments as to, for example, how the local field of these different dielectrics, for example, water, surrounded by these nanospheres, might alter molecular energetics. And in particular, we can ask the question as to, if I create a really harsh environment in this system, can I break down molecules in controllable ways? And so we're looking at PFAS. For those of you who don't know PFAS, unfortunately, you should know what they are. They're nasty chemicals. They're here to stay for a long time. They're already known to survive very long. This is a public health crisis. They're in our water. You can look at maps. Buy yourself a good filter in LA. Right now, we know that at least 48% of tap water in PFAS has PFAS, and this is probably underreported. And there's already well-reported health effects in immune liver function and cancer and what have you, right? So this is my little statement. This is a typical thing about an afterthought of a technology, right? Somebody should have thought about this before shoveling PFAS into all of our products, but now it's too late, so we got to do something about it. And this is borrowing from. I want to leave some minutes for questions. So this is the end of my slide of my presentation. This is borrowing from you can see a little bit of analogy for the system too. There is redox processes and cycles that are well understood by some chemists and, for example, people that can produce this in plasmas in harsh environments. We're trying to see whether we can recreate any of these pathways or break down a specific material. So, you have some oxidation, for example, hydrolyzation, and so on, and in a way that you can eliminate or break down a specific organic or inorganic compound. We're trying to ask ourselves at a theory and experimental level whether we can generate, we can energize these electrolytes, perhaps with nanospheres, perhaps with a strong Turret field, to either follow similar cycles of degradation or enact new ones. So again, this is super speculative. I don't have an answer to that, but we have some back of the envelope calculation and experiments underway to try to see whether we can recreate some of these redox processes with turrets as opposed to using plasmas. So with that, I have an empty, my intent was to ask the audience what the conclusions from my presentation were as a form of feedback as to anybody understood anything. But I'm happy to answer any questions or sort of zero in on any of the take-homes that I try to present on. So thank you so much for your attention. Conclusions. Yeah.
So I'm just confused a little bit about energy, about the intensity scales, because I know people, including our host here, have been producing terahertz radiation in various ways, right? And then you were saying it's very hard to make it intense. It was only intense and short. Was that the only problem?
No, I think the electron beam, and I should have a slide for this because I wanted to mention it, but then I didn't have time. I don't have that slide actually. There are ways to wriggle an electron beam using, for example, the same. It doesn't need to be an FEL, but you make your undulator longer, or you reduce electron beam energy, then you naturally will radiate turrets. I would say those are good methods to implement. They're as expensive or cumbersome, for example, as having a powerful laser, right? So I was focusing on laser-based techniques. I think some of the, if we talk about energies, I think something that we can do, for example, here, Jamie can do at UCLA, or Peter can do with, there was an Nature Photonics 2021, right? On the Staper waveguides, we're talking about, 0.1 to 0.8, 0.9 terahertz radiation based on practical ability of undulators. I'll let Jamie speak to any correction that he needs to make with microjoule level energy, which is quite good. It's we can have a conversion efficiency value for that, but generating turrets at the few microjoule level can access that strong field regime. But as you can see, some colleagues with bigger lasers can achieve already 3 orders of magnitude higher than that number. It's not easy to do, but they're not competing techniques. They're just complementary. Different ways to go about it.
I think that this is a deep question. I mean, all I can say is a millijoule is a minimum. We produced a joule of terahertz, but it took $1 billion. So, this is not a contact, or it's an easy way to do it. The question I have for you, I mean, just not to ignore all of these wonderful applications, but from my point of view, what's interesting to me is what is the frontier of creating terahertz for bringing it back to using as an acceleration radiation source.
So you're talking about terahertz-based accelerators? Yeah, well, so, some people are working on that. That was the basis of my PhD. For some reason, I'm not in the business of doing that anymore, but it's not for any, I'm joking. The idea of using terahertz radiation as an accelerator at its most basic level is simply trying to shrink down the frequency from RF to terahertz, which is taking basically more or less the same designs that you have, RF cavities, and shrinking them down because you're still operating at millimeter level things. You can still construct cavities, right? So I think there is some future promise with that. However, I do think that the types of field strength that you need to have to make that work effectively require terahertz fields that are really strong, which require really sophisticated lasers. So while in theory, looking at the accelerator components only and diminishing them in size to something more compact might seem appealing, I've also seen this promise of bringing things down to the terahertz long enough, and I worked in it personally, that the front-end technology that needs to be used to drive that, not only the efficiency and the level of energy that you need for your terahertz, but the fact that this needs to be something that works as a facility-like thing, and we're talking about jitter, time instability, and what have you. Edge is not quite there yet, in my opinion. You need Joule-class lasers to drive millijoule level terahertz to drive accelerators, and Joule-class lasers are noisy. They operate at a few hertz. They cost a lot of money. You can't just plug and play, right? So I think it'll get there. There's interesting science, but as a technology, I think there's other lower hanging fruits.
We won't give up our lifetime beat.
No, we're working on it. Yeah, absolutely. But we just got to keep a reality check.
Okay, are there any other questions and comments?
Yeah, so you mentioned during your slide demo how you basically use ultrafast X-ray diffraction to do like 3D atomic structure determination. So what is kind of like the range of samples that you can do that with in terms of size, in terms of whether or not you can crystallize them?
Yeah, so this is a tough question. I'll answer it quickly. If you have to crystallize, so the nice thing about crystallizing things is that it gives you this beautiful Bragg peaks. The reconstruction, the crystallographers have been around for a long time. This is super well established. So it's easy peasy compared to other systems. The caveat is that some people might argue that, the crystallized form of a protein is not its natural state of being. So you could push back on this Nature Chemistry paper and saying, all right, you see an inhibitor sort of binding blah, 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 but this is not how it happens in solution. So is this actually transferable to this idea of, personalized medicine, et cetera, et cetera? So there's questions around that to begin with. You can use systems that are not crystallized, but at that point you might have diffuse scatter, meaning a single element, a single shot might have its own shape, but you're averaging here over hundreds of thousands of shots. That's the reality most of the times, even with the brightest X-rays, right? So you end up having sort of average data, and you need to use really sophisticated reconstruction techniques, and you need to know a thing or two about your system to begin with, right? So there's limitations to that. Other than that, you really choose the wavelength to match the system or the elements you want to map, right? So if I wanted to look, rather than the atomic behavior within one particular protein, I want to look at the behavior between proteins, I will probably come down to a different frequency. So I can see, so my proteins are basically a ball that scatters, and I'm not seeing the individual atoms. I'm just seeing different proteins next to each other. It's always a matter of approximating everything to some sort of scatterer. And then that you can do by reducing or increasing the wavelength so that your wavelength is agnostic to fine details, or it's particularly sensitive to the dimensionality of what you want to study.
And I also wanted to ask about the reconstruction algorithms that you mentioned for, getting a single structure out of like hundreds of thousands or millions of images. How do those handle like heterogeneity, right? Because if these are at like living temperatures, they're going to be undergoing thermal motion. You know, so each one is gonna be a little bit different, right?
Yeah. So that's a great question as well. To partially answer this question, these beam times have a success rate of about 10-15%, meaning most of the times it fails. Is because you don't take all the data that usually be taken, like controlled experiments, to be able to decide that. So one way, for example, that you can overcome that in this case, there's multiple tricks. To give you an idea, you can have a control for, you can have the reason why we take multiple darks here is to have a control for the water ring is an extremely expensive thermometer, basically. Where that position of the ring is gives you some idea about the temperature of the water. And so, for example, you can include some filtering. You basically want to downsize your 200,000 images to the real 10,000 ones that are within a specific time frame, within a specific temperature. So you can do quality check in multiple ways, and that's how you rely on it. You heavily average, take a lot of data, and then you filter out 90% of your data and hope that the remaining part is useful. Yeah. Which is why going from, I didn't mention this, but LCLS, most experts work at 100 hertz level. LCLS2 will work at 1 megahertz. That's a game changer, simply because statistics. Yeah.
Okay. If there are no other urgent questions, Sergio has given us a lot to chew on, and I suggest that any further curiosities be brought up at the.
Actually, we stay here.
Oh, we stay here.
Yeah.
Okay.
Upstairs, not popular anymore. So
Not
just
popular.
like stay here. That's my question.
Okay. Okay, very good. Then we stay here.
Thank you.
Thank you so much. Yeah, appreciate it.